Hi everyone, welcome back to the channel. So today in this video we will be discussing about this interesting problem from Codeforces round 656 div 3, and it was the fifth problem of that contest and it is rated 2000. So this problem will utilize the concept of topological sorting and Kahn's algorithm. So if you are not familiar with this, please go back and study these concepts first, and once you are done you can come back and watch this video. So the name of the question is directing edges, and it reads like this: that you are given a graph consisting of n vertices and m edges, and it is not guaranteed that the given graph is connected. So the given graph can either be connected graph or can be a disconnected, right? So some of the edges are already directed and you cannot change their direction, while the other edges are undirected and we have to choose some direction for all of these undirected edges. And we have to direct these undirected edges in such a way that the resulting graph will be a directed as well as acyclic, right? And we have to do this for all the undirected edges. And we will be given with a total of t test cases. So I hope you understood the requirement. So in the input we will be given with first the number of test cases that can go up till 20,000, and for each test case we will be given two integers, that is the number of vertices and the number of edges for the given graph respectively. And for each of the m lines we will be given with three integers, that is t, x and y. So if this t is equal to 0, then it means that the given edge, that is the ith edge, is undirected. And if it is equal to 1, it means that it is directed and not undirected. And if it is directed, then it will be directed from this x of I to this y of I. And we are also made sure that the given graph will not contain self loops or multiple edges, right? So it is guaranteed that both sum n and sum m will not exceed 20,000. So in the output we have to print a no if it is impossible to direct all the given undirected edges in such a way that the resulting graph becomes a directed acyclic graph. And if it is possible, then we have to print yes. And after printing this string yes, we also have to print for each of the given edge in the graph its direction. So if 1 is directed to 2, then we have to print something like 1 space 2. And please note that you cannot change the direction of the already directed edges. And if there are multiple possible answers, we can print any of them in any order, right? I hope you understood this question. So this is the given example. So we are given with a total of 4 test cases. So as you can see the output here, for the first 3 test cases, the output is yes. And for the last one, the output is no. And since the output is no, that's why after printing no, there is no requirement to print anything further. But if the output is yes, then for all of the given edges, we have to print the direction. So for the directed edges, it will remain same as given in the input. But for the undirected edges, we have to decide that in what direction we should align those undirected edges such that the whole graph will become a directed acyclic graph. So this is the whole problem statement. So in order to understand it more better, let us understand these given examples in the blackboard. So let us now go to the blackboard. So this is the very first example given in the question. So here as you can see that a total of 3 nodes are present and 1 edge. And this one edge is directed between the first and the third node, right? So let us draw that graph here. So since there are a total of 3 nodes here, so it means that a node 1, a node 2 and the last node third will be present like this, right? And in this, an edge is present between the first and the third node, that is this edge. And since the type of the value of t given here is 0, so it means that this edge is an undirected one, right? So this is an undirected edge. So this is fairly a small example. So let us solve this quickly. So this is the whole given graph, And since it was mentioned in the question that the given graph can be disconnected, so as you can see here, this graph is disconnected. So now, if you remember, what was our task? Our task was to align all the given undirected edges in such a way that the given graph becomes directed plus acyclic. So let me write down the requirement here. So we want this graph to become a completely directed as well as acyclic graph, right? So we want it to be directed plus acyclic. So since this particular node is completely isolated, right, so there is no meaning to make it directed or acyclic with any other node because it is an isolated node, right? So we are not worried about this particular node, we are only worried about this part. So as you can see that clearly there are only two available options in order to align this particular edge. Either we can align it in this direction or we can align it in this direction. So if we try to align it in this particular direction, then what will happen? After aligning it in this direction, clearly this given graph, the whole graph, or you can say this this individual part is acyclic, right, as well as it is directed. Obvious thing, right? Or if we had directed it in this direction, then also this whole graph will become acyclic plus directed, right? So that's why in the output what we can print is, we will simply print a string yes, that is, it is possible to turn all the given undirected edges in such a way that the whole graph becomes acyclic as well as directed. So since in the input we are given just this edge, that is 1, 3, and since we can direct this edge from either 1 to 3 or from 3 to 1, so that's why there can be two possible outputs for this example, right? So either it will be yes and then in the next line 1, 3, or either yes or 3, 1 in the next line. So both of these are the possible answers for this example, right? So by directing the edge like in any one of this fashion, we will get the whole graph as to be directed as well as acyclic, right? So that's why this is the answer for this particular example. I hope you understood this. Now let us take the second example. So this is the second example given in the test case. So for this particular example, we are given with a total of 5 nodes and 5 edges. So these are the 5 edges given. So let us try to draw this graph here. So the first edge is directed from the second node to the first node here. That is like this. Then the second edge is directed from the first node to the fifth node. So something like this. And then the third edge is directed from fifth node to the fourth node. So something like this. And then the fourth edge is directed from 5 to 2 like this. And finally the last edge is present between 3 and 5. So the edge is present like this. So this is the given graph, but as you can see that I still have not yet marked the directed edges here. So let me do that here. So since for this first edge here the value of t is 0, it means that the edge present between 1 and 2 here is undirected. So this is already good. And the same is for this particular edge, that is 2 and 5. So we don't have to do anything for these two. But for the remaining 3 edges, we have to direct it in the given direction. That is, we have to direct the edge present between 1 and 5 from 1 to 5 like this. Similarly for 5 and 4 like this. And same for 3 and 5 like this. So this is the total given graph in this example, right? And for this given example, we have to find whether it is possible to align the undirected edges, that is these two edges, in such a way that the whole graph becomes a DAG, that is directed plus acyclic graph. Just by looking only, we can say that if I try to direct this edge, that is this particular edge, let's say in this direction, right? So let me mark this with some another color like this. And also if I direct this particular edge, let's say in this direction. So if I do this, then you can see that this whole graph here is directed now plus acyclic, because there are no cycles present in this graph. So this could have been a cycle, but unfortunately it's not. But since I have marked it in this direction, so it means that this is acyclic, right? And that's why the whole graph becomes acyclic. So that's why in the output we can write, first we have to print the string yes, because it is possible to orient all the given undirected edges in such a way that the whole graph is becoming directed acyclic graph. And then we have to print for each of these given edges in any order. Let us do one by one serially for each one of these edges and not randomly. So for the first edge present between 2 and 1, that is this, since we have directed it from 2 to 1, so we can write here 2 comma 1 or 2 space 1 like this. So we are done with this edge. Similarly for this particular edge, that is between 1 and 5, since it was already directed, so we don't need to do anything, right? So we will print the same thing, that is 1 comma 5. So that's why it is 1 comma 5. Now for the third part, that is 5 and 4. So since it is already directed already, so we don't need to do anything. So that's why I will write 5 comma 4 here. And then for the fourth edge, that is between 5 and 2, that is this particular edge. So since it was undirected before and I have directed it in this direction, so that's why I will write here 2 comma 5, that is the edge is getting directed from 2 towards 5. And finally for the last edge, it was already directed, so we will write it as it is, that is 3 comma 5. And that's why we can say that this is one of the possible answers of this example, and we just have to print this. So I hope you have understood this example as well. So let us now try to understand the third example. So this is the third example. So in this example, a total of 4 nodes are present and 5 edges. So these are the 5 edges given. So let us try to draw this graph here. So this is the first edge which is present between the first and the second node, and the value of t is 1, right? It means that the edge present between 1 and 2 is a directed edge. We will direct an edge from 1 to 2 like this. Next, for this given edge, it is present between the fourth and the third node, and it is an undirected one. So something like this, between 4 and 3, and it is undirected. Next, a edge is present between 3 and 1, that is something like this. And since it is a directed one, so we will keep it directed from 3 towards 1 like this. Next, a edge is present between 2 and 3, right? So like this. And since the value of t is 0 for it, so that's why it is undirected. And at last, a edge is present between 2 and 4, right? So 2 and 4, you can imagine it something like this. And since the value of t is 1, so it means that it is directed from 2 towards 4, that is like this. So I have drawn this graph here. So this is the given graph here, and for this given graph, for all the undirected edges here, that is for this particular edge and this particular edge, because these 3 are already directed, so we don't need to do anything for them. We just have to look for these 2, right? So for these 2 undirected edges, we have to orient it in such a way that the whole graph becomes a DAG, right? If I tell you to orient this particular edge, that is this edge here, in this direction, that is, let's say in this direction, and also this particular edge here, right, in this direction. So what will happen if I do this? So if I do this, then clearly you can see that this whole graph here becomes directed, right? Because each of the edge is directed now. This is directed, this is directed, this is, and this is. So all edges are directed. And our next task was to ensure that the whole graph also becomes acyclic, right? So is it acyclic? If we try to look for this particular loop here, then clearly this is not forming a cycle, right? Similarly, if we look for this particular loop, then this is also not forming a cycle. And also for this particular loop, it is also not forming any cycle. So that's why I can say that by orienting these two given edges in these directions, the whole graph has got directed as well as acyclic, right? And this is what we wanted to do. So that's why I will print a yes, and for the given edges, their direction. So whatever edges has 1 already, their direction will be same. For this first one, it will remain as same as it is, that is 1, 2. And since it was undirected before, between 4 and 3, and we directed it from 3 towards 4, so that's why I will write it as on a new line 3, 4. So we are done with these two. For the third one, it will remain same as it is, that is 3, 1. So 3, 1. For the fourth edge here, that is between 2 and 3, since we directed it from 3 towards 2, so that's why I will write it here 3, 2. And finally for the last edge here, since the value of t was 1 already, that is it was directed already, so that's why I will keep it same, that is 2, 4. And that's why I can say that this particular thing we can print as the answer for this example. So I hope you have understood this example as well. It was not that much hard to understand it. Now let us go to the fourth example, which is the last example of the given test case. So this is the fourth example here. So in this example, 4 nodes total are present. So the first edge is present between 4 and 1. So let me draw it here. So an edge is present between 4 and 1, and since the value of t is 1, so it means that it is directed between 4 and 1 from 4 towards 1. That is this. Now for the second edge, it is present between 1 and 3. That is something like this. And since it is also directed, so I will keep it directed like this. Third, a edge is present between 1 and 2. So it will be present something like this. And since the value of t is 0 here, so it means that it will remain undirected, right? And then for the fourth edge, it is present between 2 and 4. So something like this. And since the value of t is 1 here, so it means that it is directed from 2 towards 4. So something like this. And then finally for the last edge, which is present between 3 and 2, we will keep an edge between 3 and 2 like this, and it will also be directed from 3 towards 2. So like this. Now this is an interesting example, see. So as you can see here, that out of all the given 5 edges, only one edge is undirected here, right? And the remaining 4 are already directed. So whatever we can do, we can only do with this undirected edge. And clearly we only have two particular options. Either we can direct it in this direction or we can direct it in this direction, right? So if we do it in this direction, let's say, then what will happen? So after directing it in this direction, we want this graph to become a DAG, right? That is directed plus acyclic, right? So the graph is getting directed completely, right? So there is no problem in getting directed. But we also want it to become acyclic. So is it acyclic now? See, this edge is going like this, this edge is going like this, and this edge is going like this. So since this edge is going like this edge is going like this, and this edge is going like this, so clearly this is forming a cycle. So that's why it is a cyclic graph and not acyclic. So that's why orienting this particular edge in this direction is not feasible. So we will not orient it in this direction. Let us now try to explore the other possible option, which is this option only, right? So what will happen if we orient it in this direction? So is the graph directed plus acyclic now? So it is directed, yes, but is it acyclic also? Let's see. So if I try to move in this direction, so we will go from 4 to 1, and then we will go from 1 to 2, and then we will again go from 2 to 4. So this is again forming a cycle. So this part is forming a cycle. So that's why even after orienting this particular undirected edge in this direction, the whole graph is getting cyclic again. So that's why no matter what you try to do, if you orient this edge in this direction or this direction, the graph will remain cyclic. And if it remains cyclic, then the condition that the question wanted us to do is not getting satisfied. That is directed plus acyclic graph. And that's why, since it is not possible to orient all the undirected edges in such a way that the whole graph becomes directed plus acyclic, so that's why we'll just print a no. So I hope you understood this example as well, why the answer is no for this. So now the question is, when do we have to print yes and when we have to print no? So if you have read the question, then it is clearly written here that whatever the directed edges are already given in the example, you cannot change that, right? So it also means that if in the given graph, if the directed edges are already forming a cycle, then no matter what you try to do with the undirected edges, the cycle will always remain in that graph, right? And that's why the whole graph will result into a cyclic graph. So that's why we will first check with the given graph if the given graph contains a cycle or not. So that's why we will check for the given graph every time if the directed part of it contains a cycle or not. So if it contains a cycle, it means that the graph is a cyclic graph. So whatever you do with the undirected edges present in that same graph, maybe in disconnected parts, so that cycle will always remain there, right? And if it remains there, then it means that it will be called as a cyclic graph. And that's why we cannot print yes, we just have to print a no in that case. So I hope you understood this. Also, when do we have to print a yes? So if this condition is not getting satisfied, that is after checking for whole graph, or we can say for the directed part of the given graph. So if it do not contain any cycle, so as we saw in the previous examples also, if the given graph does not contain any cycle, then it will always be possible to orient the undirected edges in such a way that the whole graph becomes acyclic graph. Common sense, right? So if the given graph do not contains any cycle initially, that is the given graph is a acyclic graph considering the directed subgraph of the given graph, then it will always be possible to make the whole graph acyclic by orienting the undirected edges in some fashion. So for that case, we will print a yes. Let us try to understand the same thing using this small example here. So as you can see that this particular part of the graph is the directed part, right? Because all the edges present in this part are directed while the remaining edges are undirected. So since it is mentioned in the question that for the directed edges we cannot change their orientation in any way, right? So they will remain as it is. Whatever we can do with these two edges only, that is the undirected ones. So no matter what direction you try to align these two undirected edges, this part will remain same. And if this part remains as it is, that is a cyclic one, then it means that the whole graph will also remain cyclic and it will never become acyclic. And that's why we will print no in that case. However, if I try to change the direction something like this, let's say like this. So if the given graph is like this here, then as you can see that this is the directed part of the graph, right? Because every edge is directed here, it is acyclic because cycle is not getting formed anymore because I reversed the direction. So this part is acyclic now. And that's why I can say that the whole graph has become acyclic as well, right? So that's why it is very important to check in the very first stage whether the given graph and the directed part of that graph contains any cycle or not. So if it contains any cycle, then there is no need to check for the undirected edges because it will never be possible to orient them in such a way that this part will become acyclic because it will remain cyclic, right? So there is no need to check any further and we will print a no in that case if a cycle is already present initially. However, if the cycle is not present, then it will always be possible to orient the remaining undirected edges in such a way that the whole graph will become acyclic. So if I orient it in something like, so if I orient these two undirected edges to something like, let's say this, then the whole graph will become a DAG, right? Or if I can have arranged it to something like, let's say this, then also it will form a DAG. Or I can have arranged it to something like this. then also it will have formed a DAG. So this is what I am trying to explain. You first have to check initially if a cycle is present or not. So if a cycle is present, then we don't have to do anything further because the matter is clear. The conclusion is clear that we cannot change this cyclic part to acyclic one. And that's why we will print a no in that case, right? However, if a cycle is not present, then for all the undirected edges, which is these two edges in our case here, you can always orient those edges in such a direction that the whole graph will become acyclic. You can try it with this any other example and you will realize that what I am saying is absolutely correct. That is, it is always possible to make the whole graph acyclic by arranging the given undirected edges in such a way. Also, we will see very soon how we will print the direction of the edges once we have printed yes. But for now, important part for you to keep in mind is that we have to detect a cycle first. So we will not detect a cycle here directly. Instead, what we will do is that we will apply the Kahn's algorithm here. So if you remember what the Kahn's algorithm does, it helps to know whether a valid topological sorting is possible for a given graph or not, right? So if the final size of the array, that is the topo sort array, if it is equal to the total number of nodes present in the given graph, then it means that for that given graph a valid topological sort is possible. And if a valid topological sort is possible, then it means that the given graph is a DAG one, that is cycle is not present. So we have to print a yes. But if somehow the size of this topological sorting array, let's say it as topo sort array, right? So if the size of this topo sort array is not equal to the total number of nodes, so it will always be less than it, right? So if this is the case, that is the size of the topo sort array is less than the total number of nodes present or not equal to the total number of nodes, then it means that a valid topo sort is not possible for the given example. And why it is not possible? Because the given graph was not a DAG. Since we have ensured the surety that we are checking it on the directed part only, it means that the given graph was not acyclic. So it was cyclic, and that's why in that case we will print a no if this is the case. That is, if the topo sort size is less than n, then we will print a no. But if it is exactly equal to n, it means that a valid topo sort is possible. And why it is possible? It is possible because the given graph was a DAG. And since it was a DAG, it means that it was acyclic, and this is what we wanted. So in that case, we will print a yes. So this is the crux of this problem. Let us now try to do a complete dry run for this given example, which I have considered it by myself. So as you can see that in this example, it is very similar to the problem requirement, that is some edges are directed while some edges are undirected. So here these two edges are undirected, right? And also as you can see that there are no cycles initially present in the given graph. Let's apply the Kahn's algorithm here. So what we do in Kahn's algorithm, if you remember, we first calculate the in degree of each and every node. So if I write the in degree here for each and every node, then for the sixth node here it is 2, for the third node here it is 2, for the second node here it is 1, for the first node it is 0, for the fourth node it is 1, and for the fifth node it is 0. And after calculating the in degree, what we used to do? We used to create a queue data structure, right? And in this queue data structure, we push all the nodes which have an in degree of 0. So that's why here, since the first node here and the fifth node have an in degree of 0, so that's why we will push it into the queue. So 1 and 5 will come here. Now we will start our BFS process, and let me also write the topo sort array here, which will be filled as we move ahead. Let us try to pop the queue one by one. So first we will pop this one will come here, and then what we used to do, we used to check the neighbors of 1. So whatever the neighbors of 1, we will decrease their in degree by 1, and we will see if that is getting 0 or not. So if the in degree is getting 0 after decreasing it by 1, we will push it into the queue. Simple. So since here the neighbors of 1 are 2 as well as 3, but not 4 and 5. Now you will ask why? Because according to the example that I have considered, this 4 is a neighbor of 1 and this 5 is also a neighbor of 1. But what I told you, we are applying Kahn's algorithm here, right? And the Kahn's algorithm only works on a directed acyclic graph, right? That is directed. So as I have told you during the example explanation also, that whenever we will apply the Kahn's algorithm, we will only apply it for the directed part. So you have to imagine it something like these particular two edges do not exist as of now. So in this graph, we are applying the Kahn's algorithm actually. So for now, let us erase these two edges and work on this graph in which the given undirected edges are not visible. Once we have popped out one and inserted it in toposort, so now we are checking the neighbors of 1 which are connected to it directly through a directed edge and not an undirected edge, right? So since this second node and the third node are present as the neighbors of this first node, so we will decrease their end degree by 1. So that's why the end degree of this 2 will now become 0. Similarly, the end degree of this 3 will now become from 2 to 1 like this. And since after doing this, the end degree of 2 has got 0, so that's why I will push it into the queue. So this 2 will now go into the queue. Now let us move forward. So we will pop this 5 here and place it in the toposort, and now we will check the neighbors of 5 which is connected to 5 directly through a directed edge. So since this 4 is connected to 5 directly through this directed edge, so we will decrease its end degree by 1. So if I decrease the end degree, then it will go from 1 to 0. And since it is getting equal to 0, it means that we have to push this 4 into the queue now. We will insert this 4 here into the queue. And since there are no any other neighbors other than 4, so that's why we will now move forward with the next element present at the front of this queue, that is this 2. So after popping this 2, we will push it into the toposort array, and then we will look the neighbors of 2 which are connected to 2 directly through a directed edge. So as you can see that this edge and this edge are connected directly to 2, right? So we'll decrease the end degree by 1. So the end degree of 6 will now become from 2 to 1. Similarly, the end degree of 3 will now become from 1 to 0. And since it is getting equal to 0 after decreasing it, so that's why we will now push this 3 into Q. Now let us move forward and pop the next element. So the next element is 4, and if we talk about 4, then clearly it has no neighbors through which it is connected directly through a directed edge, right? Because it has to go something like this, but it is not. So that's why we will again move forward. And the next element present here is 3. So we'll pop 3. So it will come here. And now we will look into the neighbors of the third node. So since this is the third node, and through a directed edge, it is only going towards 6, which has an end degree of 1 remaining. So that's why we will decrease the end degree of this 6th node from 1 to 0. And since it has got 0 now, so we will push it into the queue. So 6 will come here. And if we move forward at last, then only 6 is remaining into the queue. So we will pop it out. 6 will come here. And this 6 will now see that what neighbors it is connected to directly through a directed edge, but it is not connected to any directed edge, right? To any other node through a directed edge. So we will stop it here. So in this way, we have got this particular toposort ordering. So if you calculate the total number of elements present in this toposort order, so it is total 6 in number, right? And also in the given graph, a total of 6 nodes are present if you count 1, 2, 3, 4, 5, 6. So since the total number of nodes present in the original graph is equal to the total number of elements present in the final toposort array, and this gives us the confirmation to print a yes. I hope you understood what I just did. Let me explain you briefly once again. So what I did was very simple. Initially this was the given graph in which these two edges were also given, which were undirected. And I told you that the condition when we have to print no will only be possible if the given initial graph contains a cycle. So in order to detect a cycle, what I told you is to apply Kahn's algorithm, because after applying Kahn's algorithm, we will get a toposort array, right? And in that toposort array, by looking at the total number of elements, we can determine if the given directed part of the given graph contains a cycle or not. So if the total number of elements are matching with the total number of nodes, then it means that we have got a valid toposort ordering, and it has become possible because the given graph was a DAG, that is directed acyclic graph. So the graph was acyclic. So we can determine it through this. And that's why we will print a yes in that case. However, if the total number of elements present in the toposort array was not equal to the total number of elements, it means that a valid toposort ordering was not possible. In that case, we would have printed no. But before moving ahead, let me also tell you how we will actually print or orient these two undirected edges now. That is how we will decide whether we have to orient it from 1 to 4 or from 4 to 1, or we have to orient it from 1 to 5 or from 5 to 1. So as of now we have printed yes, right? And now we want to direct all the edges. So since I have already told you that for the directed edges it will remain same, we don't have to do anything, right? So we will write for this 1 and 2 as 1, 2, for this 1, 3 as 1, 3, for this 2, 3 as 2, 3, for the 2, 6 as 2, 6, and for this 3, 6 as 3, 6. But the thing is now how I will decide it for these two undirected edges. So it is very simple. See, so suppose 4, 1 was given in the edges part in the input, right? 4, 1 was given, suppose. And more precisely if I say, then it would have been given as 0, 4, 1. And now we want to determine whether the DAG is going from 4 to 1 or from 1 to 4. So we will just look into this ordering for this fourth node and the first node. So the first node is present here and the fourth node is present here. So since 1 is coming before 4, in this topological ordering, right, 1 is coming before 4. So it means that 1 has to be directed towards 4, like this. Similarly, if in the input we are given with 0, 1, 5, so we will just look in this valid topological sorting order for these 1th and 5th node, that is this and this. So since 1 is coming before 5, so it means that 1 has to be directed towards 5, like this. So in this way 1 has to be directed towards 4 and 1 has to be directed towards 5. And by doing that, we will just print the same, that is 1, 4 and 1, 5. And this is the whole thing that we wanted to print it. I hope you really understood what I just told. So what I did was very simple. I just checked for the given graph initially that if it contains a cycle or not. So if it contains a cycle, then no matter what you try to do with the undirected edges, it will remain cyclic. So there is no way we can turn it into acyclic, and that's why we will print a no in that case, right? Simple. And if it is not the case, that is initially there are no cycles present, that is the given graph is an acyclic graph. So if it is acyclic graph initially, it means that we can orient the remaining undirected edges in such a way that the whole graph will remain acyclic. So in order to deduce in what direction we should align the given undirected edges, I told you that we will just utilize the toposort array that we obtained through Kahn's algorithm. So let us now go to the code editor and code the logic quickly. So in the input, first we have to take the inputs for n and m. So n and m, that is the total number of nodes and the edges respectively. Then we have to take input for the m edges, and for each of the line we are given with 3 integers, if you remember, that is t, x and y. So if the value of this t is equal to 1, it means that the given edge, that is this ith edge, is a directed one. So we have to direct it from x to y, right? So it is a directed edge. So that's why I will say g of x dot push back y. So let me declare this adjacency list here outside. So vector of this, let's say it long only. So I will be using one based indexing only here. And since later we also want to utilize the information during orientation of edges, whether the given edge was a directed or undirected one, so that's why we will store it separately in another vector. So it will be something like edges dot push back, first the type of orientation and then the pair, that is x, y. So this. So once we have written this, our next task is to apply Kahn's algorithm, right? So apply the Kahn's algorithm in order to find in order to find whether the given graph initially, that is the directed part of the given graph, contains any cycle or not. Right, so what we do in Kahn's algorithm, if you remember, we take a Q data structure, and in this Q data structure we check for all the nodes which have an in degree of 0. So we will visit each and every node from 1 to the last nth node, and we will check if the in degree of this ith node is 0 or not. So if it is equal to 0, then we will simply push it into the queue, that is q.push I. So in order to store the in degree here, I will declare another vector like this, and this will also be 1 based indexing only, so n plus 1. So I will say in degree of this y plus plus, right? So once this has been done, I will begin my BFS process. So until the queue is not empty, I will pop the front element, so that is the node present at the front, that is q.front, and then I will do a q.pop, and whatever has been popped out, I will store it into a valid toposort array, or rather I should call it a toposort ordering array, right? So that's why I will name it as, let's say, toposort, just a toposort. So I will write here toposort.pushback this node, and after storing it we will look into its neighbors. So if this C is a neighbor of this node, then we will decrease the in degree of this C by 1, and after decreasing it, if the in degree of this C becomes 0, then we will simply push it into the queue, that is q.push C. And after this while loop has been completed, we will simply check if the size of this toposort array is less than the total number of given nodes or not. So this is toposort, right? So if it is less than the total number of nodes, it means that a valid toposort isn't obtained. And why it is not obtained? It has not been obtained because of only one reason, and that is the graph given isn't DAG. So if it is not DAG, then what it is? It is a cyclic graph. And if it is cyclic, it means that we can never make it acyclic, because it has been told in the question that we cannot touch the already given directed edges. So that's why we have to print a no here and simply return. But if this is not the case, that is the toposort size is equal to n, that is we have got a valid toposort, that is a valid toposort is indeed obtained. So if it has been true, then if it is true, then it means that a valid toposort is obtained just because the graph given is a DAG, that is it is acyclic. And if it is acyclic, then we have to print a yes. And after printing yes, we also have to orient the given edges in some direction, right? And more particularly only the undirected edges, because the orientation of the directed edges will remain same. So in order to do that, we will simply iterate through this edges array that we just stored here, and I told you that we will utilize it later on. So we are utilizing it now. So I will say here, for auto IT belonging to this edges array, this it dot first is my t, this it dot second dot first is my x, and this it dot second is my y, right? So if this t is equal to 0, then it means that this was an undirected one, right? Otherwise it was a directed one, right? So if it is a directed one, then we don't have to do anything, we just have to print it in the given order, that is x space y, right? But if it is undirected, then what we will do, we will check the position of this x and y in this toposort array. In order to do this, we have to know the index position for each of the nodes, right? So let us do that here. We will store it here only. So I will just simply iterate through this toposort array once. So I will simply iterate through this toposort array once. And I will say that the index for this toposort of I is equal to I. And let me declare this array here, that is the index array. So by doing this, we can determine the index position for each of the node in the toposort array, right? And now we will utilize it here. So I will check if the index position of this x is less than the index position of y. So if it is true, then it means that x is present before y. That is, we have to direct from x towards y. That is, first x will come and then y. So I will write first x, then space, then y. And if it is not true, then it means that y is coming before x, and if y is coming before x, then it means that first we have to print y, then x. So this, and finally just do a return statement because it's a void function. And since there are multiple test cases, so I am just doing uncommenting this. So I think I have written the complete code here. So let's try to run the test cases here and see if it is working fine or not. So as you can see here, we have got the outputs here, and obviously since multiple answers are possible, so it is not matching with the given expected output, but this is not an issue. Let's try to submit it onto the platform to see if we are correct or not. So as you can see that our solution is accepted completely. This is the code that we just wrote, and I explained you each and everything in very detail. So I really hope that you understood this problem, and I tried to explain it in the simplest way possible. So if you think you understood something new and informative, please consider liking this video and subscribing this channel, because it takes a lot of efforts to create each and every single video. So thank you so much for watching the video. Thank you.